This is Jennifer Vasquez, your presenter. Welcome to Chemistry. In this video, we're going to learn about the effective nuclear charge and the periodic trends in the properties of elements. So now let us first define what is effective nuclear charge. Effective nuclear charge is the average nuclear charge felt by an electron in an atom, taking into consideration the shielding effect of inner shell electrons. Take note that the effective nuclear charge is equal to Z minus S, where Z is the number of protons in the nucleus and S represent the inner shell electrons. Remember also that the number of protons in the nucleus is same as the atomic number, which can be easily found in our periodic table. So now let us try to determine the number of inner shell electrons. So let's have an example. Now the question is, what is the effective nuclear charge felt by an electron in the n equals 4 shell of sulfur? The atomic number of sulfur is 16. Therefore, the number of protons in the nucleus is 16. Now let us start diagramming the proton around the nucleus of sulfur. Remember that the n equals 1 of sulfur can hold 2 electrons. The n equals 2 shell of sulfur can hold 8 electrons. So we already diagrammed 10 electrons, right? So the n equals 3 shell of sulfur can hold 14 electrons. But since sulfur have only 16 electrons and we already diagrammed 10 electrons, so there are 6 electrons left to be put on the n equals 3. So in order for us to get the effective nuclear charge, we're going to subtract the number of protons in the nucleus less the number of inner shell electrons. So 16 less 10 is equal to 6. Therefore, the effective nuclear charge of sulfur is 6. Now let us move on the periodic trends. Periodic trends have 5 different trends. Let us start in electronegativity. Electronegativity tells us how well an element can attract electron. Now let's have an example. Which element is the most electronegative? Is it chlorine or oxygen? It's quite difficult, right? Because as we can see, chlorine and oxygen have the same or equal distance to fluorine. But in this case, the higher up is the most electronegative. So that is oxygen. Now the next periodic trend we will talk about is the ionization energy. Ionization energy required to remove an electron from its orbital of an atom. Take note that the valence electron farther away from the nucleus, the easier it is to pull it out. Okay? On the opposite side, the closer or the closest valence electron to nucleus, it cannot be easily pulled out because they are stable. Take for example the francium. The francium is a very large atom with one valence electron. So it's easy to ionize because the valence electron is very far from the nucleus. On the other side, the helium. The helium has only one shell and 2 valence electrons. So the valence electron is very close to the nucleus, so they are stable. So it needs more energy to ionize the helium. So it's not easy to pull out. The trends of the ionization energy is similar to electronegativity. It increases when it goes up and moves across the periodic table. Let's have an example. If we're going to compare the sulfur and chlorine, which is the highest or the most ionization energy? So what element is more closer to fluorine? So it's sulfur. So the most ionization or the highest ionization energy is sulfur. There is also an exemption here. Take for example sulfur and oxygen. These two have the same distance to fluorine. In electronegativity, the higher up is the most electronegative. But then in ionization energy, it's different. It cannot be determined. So we are now in electron affinity. Electron affinity is opposite from ionization energy. Remember that ionization energy required to remove an electron, electron affinity required to add an electron. The trends of this electron affinity, it increases when it moves up and move across the periodic table to the right or to the fluorine side. So there is also an exemption here. given that the trends of electron affinity is that it increases as it moves up and move across to the right side. But in this case, if I'm going to compare one of the elements in group 1 and 2, take for example lithium and beryllium, beryllium has a lower electron affinity. We are now on the atomic radii. Atomic radii is one half distance between the nuclei. What we are measuring in atomic radii is the distance. The chance of this atomic radii is completely different or opposite from electronegativity, ionization energy, and electron affinity. The chance of this increases when it moves downward and move across to the left side. Next is ion size. Remember that an ion is simply an element with a charge. It can be cation with positive charge and anion with negative charge. Ion size increases as we move down the column. The term isoelectronic refers to the same number of configuration and same number of electrons. So let us have an example. If I'm going to compare sulfur with neutral charge and sulfur with 2 minus charge, okay, the first thing that I'm going to do is to determine how many electrons does sulfur have. So sulfur have 16 electrons. So in sulfur with neutral charge, I'm gonna put 16 electrons. And in sulfur with 2 minus charge, so since it's 2 minus charge, it means we're going to add electron because electrons are negatively charged. So therefore, we can conclude that an ion or ion with negative charge has a bigger atomic size in this case. Now the last one is the metallic character. Metallic character is how closely an element's properties match those of a metal. So we are looking on a metal. What are the properties of a metal? What is a good metal? So a good metal should be malleable, good conductor, ionize easily, okay, shiny, and is going to reflect light. Now let's have an example. If I'm going to compare antimony and phosphorus, which of these two has the higher metallic character? So as we can see on the periodic table, antimony is lower than phosphorus. Therefore, we can conclude that antimony has the higher metallic character. That's all our lessons about effective nuclear energy and periodic trends in the properties of elements. Thank you for watching.